we go. So guys, this is what we're doing today. Anybody want to take a swing at pronouncing it? Not even close. Stoichiometry. So guys, when you go home tonight and you're gathered around the dinner table with your family, I want you to say the word stoichiometry out loud to your parents, and then they will believe that they're actually getting their tax money's worth in your education. Because you can say, guess what, Mom and Dad, or whoever's at the table, I learned about stoichiometry, and then you sound rather intelligent. So, guys, this is the way this is going to go down. And it sounds crazy, but in learning something with as impressive a name as stoichiometry, you're not going to learn anything new today. Let me explain to you why. So guys, the question is, what is stoichiometry? You ready? Don't write this down, but this is stoichiometry. It goes like this. So guys, moles conversions, right? Everybody's now done taking the retest over this. This was the content of the entire last unit, the T-chart, grams and moles and particles and Avogadro's number. Remember all of that stuff? So guys, moles conversions, the entire last unit, and then this entire unit. We have now spent 3 days writing balanced equations. We learned to balance them, we learned the reaction types, and we just did a lab. So this is the way this goes. Take everything that you know about moles conversions, take everything that you know about balancing equations, and bring them together, and guess what comes out? Stoichiometry. Guys, that's what stoichiometry is the math of balanced equations. So this is the technical definition you need to write down. So guys, stoichiometry, you know what? That doesn't mean anything to you. Let's do this. Let's change it. The math of chemical equations. That's the best thing about being a teacher. You can make up your own definitions. All right, there you go. Have you ever thought about that? None of you are in a position to make up your own definitions. But if you become a teacher, then you can make up your own definitions. Because who gets to decide what definitions work? The guy that's writing the test. I like it. All right. So, guys, again, stoichiometry is the math of chemical equations. So, in order to understand stoichiometry, this is what you really need to understand. These are what are called stoichiometric ratios. Stoichiometric is actually the adjective form of stoichiometry, the noun. So, that's fun to say. It kind of tickles. Stoichiometric ratios. So guys, what is a stoichiometric ratio? Well, here's the thing. You've been doing stoichiometric ratios all along in this unit. So let me define it for you. A stoichiometric ratio is the molar ratio of one reactant or product to another product or reactant in a balanced equation. So guys, the bottom line is when you have been balancing equations, you have been creating stoichiometric ratios. You just didn't know it. So let me show you an example. Guys, scratch this one in your notes just so you have an example. And then the next one I'll show you just to make sure you understand it. You don't need to write that one down because if you get one, you'll get them all. It's pretty straightforward. What's that? What does? Oh, the equal sign? Oh, yeah. So it's funny. I'm glad you caught that, Landon. We haven't talked about this yet. See this arrow that goes in both directions? Guys, I didn't even notice I did that. I just did it right and didn't think about it. Guys, this reaction is interesting. Up until now when we've been writing reactions, we have an arrow that points at the products, right? This is actually what we're going to talk about in the next unit. This is actually a reaction that goes in both directions. the nitrogen and the hydrogen become NH3, but the NH3 then breaks apart and turns into nitrogen and hydrogen, and it goes in circles and never stops. We'll talk about it more in the next unit. But guys, the basic idea is this. So here we've got nitrogen, hydrogen, and then NH3, which is ammonia. The question is this: how much nitrogen do we have? 1. How much hydrogen do we have? 3. How much NH3 do we have? 2. That is the stoichiometric ratio. And here's what it means. For every 1 mole of nitrogen that we put in, that will react with 3 moles of hydrogen, and it will make 2 moles of NH3. So this 1 to 3 to 2 ratio, the stoichiometric ratio from the balanced equation, is a molar ratio. So it's 1 to 3 to 2. You get the idea? So guys, what about this then? The synthesis of water. And you know what? This is wrong now. Gosh, Landon, I'm so glad you caught that. This is the wrong arrow. We got to get rid of that. Show emojis frequently used. This arrow, that's the wrong one. This one doesn't. Oh gosh, don't do that. Please don't do that. This one doesn't go both directions. Here we go. Okay, so let's put that back up. And guys, what about this reaction? The synthesis of water. What is the stoichiometric ratio? 2 to 1 to 2. You get it? That's all there is to it. So guys, you put in 2 moles of hydrogen, you put in 1 mole of oxygen, you get out 2 moles of water. Those are stoichiometric ratios. You get the idea? So what are we going to do with them? Well, guys, what you're going to learn to do today is something like this. And then this is the lab we're going to do next week. Not this particular one. But we now understand that it's a 2 to 1 to 2 ratio, right? So we're going to be able to answer questions like this. Say that you take 25 grams of hydrogen and you burn it up in our oxygen atmosphere. How much water will it make? It's not 25 grams. Even though this is 2 to 2, it's not, the answer is not 25 grams. Why not? Because hydrogen and water don't weigh the same. So what you're going to find out we've got to do is convert 25 grams of hydrogen to moles. Then we can talk about that 2 to 2 ratio, and then we can convert back to grams. Because those are the kind of questions we're going to ask. If you put in 25 grams of hydrogen, how many grams of water will you get out? And guys, there's a name for these problems, and this is what we're doing today. These are what are called mass problems. This is the last of your notes today. We're going to solve 2, and you're going to have probably 40 minutes to work on your homework. And guys, just so you know, my board is doing so poorly that I actually sat down last night and I animated all of my slides. So instead of me trying to write the solutions to these, I just animated it and did it electronically because my board is, they're actually sending somebody out from Colorado next week to try to come and fix it. So anyway, so mass problems. They go like this. So a mass problem, guys, is a stoichiometric process. What does that mean? It just means balanced equation stuff. So it's a stoichiometric process that allows you to figure out how much reactant or product is created or consumed in a chemical reaction. And what you're going to find out, guys, is that there's 4 steps to these problems. And the steps are always the same. It's dimensional analysis. But the dimensional analysis becomes very repetitive because it's the same 4 steps. It is nice, yeah. So guys, the steps go like this. Step number 1 is what we've learned in this unit. Write a balanced equation. Then steps numbers 2, 3, and 4 are what we learned in the last unit, the dimensional analysis. So write a balanced equation, then convert mass to moles, apply the stoichiometric ratio, and then convert moles to grams. So that's it, gang. You're done taking notes. We're going to solve 2 of these, and then you're going to have time to work on these. It's really the way to learn them is by doing them. Can you guys tell that the text on the screen is shaking? Can you guys see that from a distance? You can't. Is it, well, had you noticed if I hadn't mentioned it?
It was shaking the other day. So.
Oh, that's true. Because like when I get right up against this, you can actually see the letters shake. But I don't think it's because the wall's shaking. I think it's because the projector's weird. Maybe I'm just angry with this projector. You ever found yourself angry with a thing? Realizing it does absolutely no good because it's a thing, right? I'm angry with that. All right, you guys all caught up with me? You're good? So guys, let me ask you a question. If you really understand what you just wrote down, see if you can answer this question. Why do we call these mass problems? Yeah, guys, look at where you start. You start, oh, whoa, that wasn't supposed to happen. I'm trying out new software to see if I can get things to write better. And, oh gosh, and now it's gone. Now I can't write it. Oh, it died. Died? Died. It died dead. Oh, wait, it's back. It's back. That makes it a zombie. Wait for it. Here we go. Come on, will you let me write? I just want to write. That's it. This is what you do. This is why you... I'm so glad I animated today's slides. Okay, so guys, I can't write, but I can at least talk you through it. So guys, why do we call these mass problems? Because the dimensional analysis starts with a mass and it ends with grams, which is a mass. So guys, when you do this dimensional analysis, you will always start with a mass and end with the mass. That's why we call them mass problems. So, with that said, this is how they read. I would encourage you to write it down. So guys, it goes like this. It says, how much water will you produce when 12.5 grams of methane are consumed in a combustion reaction? So guys, methane is Bunsen burner gas. So if you could weigh out 12.5 grams of Bunsen burner gas and light it on fire, how much water would you get? That's the question that we're asking. So guys, if you're curious, how much is 12.5 grams of methane? And the answer is about 9 2-liter bottles. If you can picture that. So if you have 9 2-liter bottles of Bunsen burner gas and you lit them on fire, how much water would you make? We're going to figure it out. So guys, here's how we go. What's the first thing we need looking back at the steps? Balanced equation. We have balanced this equation numerous times, so I'm just going to give it to you. All right, so now guys, what is step 2? Well, it's a mathematical step, and it says convert grams to moles. But guys, if we're going to convert grams to moles, we need a number of grams. So what is the mass that we're given that we can start with? 12.5 grams of CH4. Now, guys, let's not forget what we learned about dimensional analysis. And actually, we're sort of doing this backwards a little bit. We should have started with our goal, but we're okay. So what do we need to do next? Draw a line. And then finally, we need a goal. Now, guys, if you look at the steps, we understand that our goal in a mass problem will be a mass. But the mass of what? What are we trying to figure out the mass of? How much water? So our goal is grams of water. And guys, once you get to this point, this is where these become wildly redundant. They're always the same 3 steps. So the next step is step number 2 in the steps. What are we going to do with this mass? Convert it to moles. So guys, carbon weighs 12, hydrogen weighs 1, 4 times 1 is 4, plus 12 is 16. So when we convert this to moles, does the 16 grams go on the bottom and the top? Of course, the bottom. So 16 grams is 1 mole of CH4. So now we've converted to moles of CH4. Now, guys, this is the only new part that you're learning today. You already know moles conversions. You already know balanced equations. The only thing that is slightly new is the mole-to-mole ratio, which is step 3 in the steps. And watch how to do this. Guys, if this is moles of CH4 up here, what's got to be down here? Same thing, moles of CH4. But write it like this. Go blank moles of CH4. Now, guys, this is the thing that's a little different. What's going to go on the top? And the answer is moles of your goal. So that will be moles of water. Now, here's the question, the learning point. What goes in the blanks? Well, guys, the numbers that go in the blanks are the stoichiometric ratio from the balanced equation. So what is the number in front of CH4 if there's no number there? It's a 1. And then, guys, what is the number in front of the water? It's a 2. So now we know it's a 1 to 2 stoichiometric ratio. For every 1 mole of CH4 that we put in, we'll get out 2 moles of water. Now, guys, to finish this up, it's just like the good old days. Can we go from moles of water to grams of water? You bet. Hydrogen weighs 1, oxygen weighs 16. Add those up, and 1 mole of water is 18 grams. So now, guys, we do the math, and we go 12 divided by 16 times 2 times 18. And it looks like we get 3 significant digits. And if you run the numbers, I get 28.1 grams. Because I did this late last night, you may want to run the numbers and make sure I'm right. Is that right? Cool. So either Landon and I are both wrong, or that's really the answer. So guys, in the end, what does that mean? Well, it means if you burn up 9 2-liter bottles of methane, you get out 28 grams or 28 milliliters. So in our graduated cylinders, it'd be about that much water. It's at least a couple mouthfuls. What do you think? You get the idea? You get the process? Okay. Now, guys, here's the thing that's interesting about this process. You don't always have to start with a reactant, and you don't always have to solve for a product. You can do any possible combination, which you're about to see right here. So it says how much copper 2 nitrate will be consumed when 10.2 grams of sodium chloride is reacted with it. So guys, we'll solve this and then you're going to have lots of time to do your homework. You may not even, well, I don't know. You may get it done. Maybe. Y'all, can we go for it? Okay, so guys, what's step one? Balanced equation. Now, in the previous problem, I just laid the balanced equation on you because we had balanced the combustion of methane like 11 times. But guys, I'm not going to do that here because this is a reaction we've never seen before. So we've got to write the balanced equation, which is everything you've learned to do over the last couple days. So guys, if that's the case, remember the strategy. What's the first thing that you do when you're trying to write your own balanced equation? What do you put on the paper? An arrow, right? Always start with the arrow because the arrow says everything on the left is a reactant and everything on the right is a product. Now what do we do? Well, guys, now what we've got to do is read through this thing and figure out what's reacting together. So it says how much copper 2 nitrate will be consumed. And guys, if it's consumed, that means it's a reactant. So now we've got to figure out what copper 2 nitrate is. So guys, copper 2 nitrate is CuNO3 Copper's plus 2, nitrate is minus 1. Off we go. Now, gang, what is that reacting with? Our good friend, sodium chloride, says when 10.2 grams of sodium chloride is reacted. So, guys, we're just reacting this with table salt. So now what we've got to do is figure out what our products are. Can you look at this from a distance and figure out what kind of reaction it is? Maybe we should talk. Can it be single displacement? No, it's not an element in a compound. Can it be double? Yeah. Synthesis? Could be. Can it be decomposition? No, there's more than one reactant. Can it be combustion? No, it's not a hydrocarbon plus oxygen. So it's either double displacement or synthesis. So guys, let's talk synthesis. Can we jam all those together into one product? No. So it's double displacement. So guys, again, and please hear this, if you don't learn anything else today, guys, if you need to figure out the products of a single or double displacement reaction, what do you need? Charges. Copper's plus 2, nitrate is minus 1. And then, guys, sodium is plus 1, chlorine's minus 1. So, who hooks up with whom? So, copper is going to go with chlorine, right? Plus and minus. Copper's plus 2, chlorine's minus 1. So, what are we going to get? CuCl2. Notice, guys, the chlorines don't balance, but they're not supposed to. Then, guys, our other product will be sodium is plus 1, nitrate's minus 1. You need one of each, sodium nitrate. So now, gang, when we balance the equation, we've got 1 copper, 2 nitrates, 1 nitrate. So we need a 2. Then 1 sodium, 2 sodiums, so we need a 2. And then that gives us 2 chlorines on each side. Is that groovy? So now, guys, we've got to set up the math. Steps 2, 3, and 4. Start with the mass. Set your goal at the mass of what you're solving for. Do the math. So, guys, what mass are we going to start with? 10.2 grams of sodium chloride. Draw yourself a line. And what is our goal? Grams of what? How much copper 2 nitrate? So our goal is grams of copper 2 nitrate. All right. At this point, guys, this just becomes this repetitious process, grams to moles, moles to moles, moles to grams. It's the same thing every time. You don't have to think. You don't have to strategize. You just got to go grams to moles, moles to moles, moles to grams. So let's go grams to moles. Sodium is 23, chlorine's 35.5, 38 or 58.5 grams of salt is 1 mole of table salt. Then, guys, the one little bit that is new, and that's the moldable ratio. Remember, what we do is we go blank moles of our starting point on the bottom. We go blank moles of our goal on top. And then, guys, all you got to do is go get the numbers out of the balanced equation. What's the number in front of NaCl? It's a 2. What's the number in front of copper 2 nitrate? Nothing there. It's a 1. And then, guys, the last step is always moles to grams. Copper weighs 63.5. Nitrogen is 14. Oxygen is 16. Do all the math, and 1 mole of this weighs 187.5 grams. Then, guys, from there we just do the math. So 10.2 divided by 58.5 divided by 2 times 187.5. Looks like we get 3 significant digits, and that would be 16.3 grams. So, guys, here's the way this is going to play out. On Tuesday, when I see you again, we're going to grade this, and then we're going to add one more little twist to this process. Then on Thursday, you're going to go into lab, and you'll actually be given a fixed amount of a reactant, and you're going to collect the product, having predicted how much product you should have collected, and then you're going to do something kind of like percent error. You'll see on Tuesday. But guys, that's what's coming down the road. But for now, you need to get good at these. So if you grab the homework, which you've already got in front of, well, you should, the homework packet, guys, turn to the page that says number 3 at the top. Does anybody need a copy? You're all okay? Okay, so notice what it says, guys. Stoichiometry Homework. So let's just go through this. In numbers 1 and 2, I gave you the balanced equations. In 3 and 4, I did not. Then in 5 and 6, I gave you the balanced equation, but guys, that same balanced equation works for numbers 5 and 6. Then, guys, number 7 is kind of out of left field, right? You're like, whoa, what's going on here? Guys, number 7 says classify these reactions as single, double, synthesis, decomposition, combustion. So you're like, wait a second, that's kind of weird. The reason that I did that is because, guys, these equations in number 7 are the balanced equations for 8 through 13. They're not in order, so you're going to have to read them to figure out which one is the right balanced equation. But guys, but the equations in 7 are the balanced equations for 8 through 13. So guys, the bottom line is the only ones of these where you've got to do what we just did on the board and write your own balanced equation, the only place you'll be doing that is 3 and 4. So guys, you have the remainder of the day to work on these. I will put the answers on the wall. Good heavens, you have 40 minutes. So there's a very real chance you'll get these done. Dig in, go get them.